everyone. I think we're going to get started right on time. And so our next speaker is Ofir Nachum. And Ofir is going to tell us about attacking the off-policy problem with duality. Take it away, Ofir.
Right, thank you. Yeah, so I'll be, like the rest of the talks today, I'll be talking about off-policy learning. But unlike those previous talks, I'll be discussing an approach based on convex duality. So I'll just get it right into it. And so here's the setting I'll focus on. It's an MVP where your policy is pi, and it starts each episode at some initial state given by some initial state distribution, u0 here. At each step, it produces an action, which the environment uses some reward function to turn into an immediate reward, and then uses some transition function to transition to a next state. And in the off-policy setting, we typically only have access to historical logged experience data. So we might have access to the things in blue, but we don't have explicit access to the things in black, whether it's the initial state distribution or the transition or the reward functions. But in this section, in this setting, we still want to do some sort of reinforcement learning, some sort of policy evaluation, policy optimization, or other things. And so the problem is, how do we actually do these things? How do we do reinforcement learning in this off-policy setting? And there's a number of challenges presented by this setting. In this talk, I'll focus on two of them, which arguably are sort of related, but for now, I'll just talk about them as two different problems. So the first one here is the distribution shift problem, which refers to the fact that the off-policy data set you have access to was sampled or gives you a distribution over state actions, which is different from the on-policy distribution you usually want when performing Monte Carlo samples or when performing on-policy policy gradient. And then the second big challenge is what I'll refer to as the generalization problem. And this refers to the fact that in the off-policy setting, you necessarily have limited data, or your data only covers a small subset of the state and action space. And so this limited data exacerbates existing extrapolation and generalization issues in standard RL algorithms. And this is why we get things like exploding Q values and divergence in training and things like that. So in this talk, I'll talk about how to approach these two problems. And specifically, I'll explain an approach based on convex duality. So what I'll start with is the LPs. So I'll show a linear program where the primal LP corresponds to Q values of some policy, and the dual LP corresponds to d pi, which I use to denote the on-policy distribution of pi. And then what I'll show is that we can actually approach those two challenges I mentioned using convex regularizers. And specifically, I'll show how the distribution shift problem can be approached by regularizing dual variables. And analogously, I'll show how the generalization problem can be attacked by regularizing the primal variables of this LP, and then using a bunch of convex duality applications to yield objectives which are practical and applicable to off-policy stochastic settings. Okay, so let's get started. So RL as an LP. So there's a bunch of LPs you can use to express reinforcement learning problems. In this presentation, I'll focus on what I call the QLP, which is a way to express the value of a policy, which I read as this rho of pi function, as a linear program, where you can see why it's called the QLP, because the variables are Q values. And the objective here is the expected initial Q values. So the expectation here is over state sampled from the initial state distribution, and then initial actions sampled from your policy. So we have this objective, and then the constraints are actually the standard Bellman operator we're used to with respect to policy pi. So the constraints say at each state in action, your Q value should be at least the immediate reward plus gamma times the average next Q value. Well, I've used this p pi operator to represent this expectation over next Q values. So this p pi is just you can think of it as just the transition matrix under policy pi. So we've got all these inequalities, and actually this objective, which is a minimum, pushes all the Q values down and turns all these inequalities at the optimum to equalities. And once you get equalities here, it's easy to figure that the Q star should be exactly Q pi, the Q values of pi. And then when you stick Q pi into this objective, the average initial Q pi values is exactly the policy value. So this is the QLP in its final form. And then naturally it has a dual form, which yields the same result, the policy value, but in a different manner. So you can see instead of Q values now, we have these D variables, which you can think of as a distribution. And the constraints are no longer the standard Bellman operator constraints we're used to. Instead, they're what's called the transpose Bellman operator, or you can think of them as flow constraints. And flow in the sense of probability, because these equalities exactly express the flow that the stationary distribution of pi has to satisfy in order to be aligned with the transition matrix of pi. And so these equalities actually express the conservation of flow of a probability distribution under transition dynamics determined by pi. And so the D variable has to be exactly d pi, the on-policy distribution, according to these constraints. And once you figure that d star has to be d pi, you can stick it into this objective, and you get the sum of d pi times r, which is exactly the expectation under the on-policy distribution of rewards, which is your policy value again. So these LPs are nice, but they're not immediately useful to us. And the reason is because of all those constraints. So those constraints in either the primal or the dual, a constraint for each state in action, and these constraints are difficult to handle in the settings we're used to, the off-policy settings we're used to. And so like I mentioned in the outline, what I'll describe is how to apply convex duality to these LPs. So what we'll do is actually utilize convex regularizers, apply them to these LPs, and then use duality, and that'll actually yield us a more tractable and unconstrained objective. And what I'll show you is that there's a lot of choice in what regularizer you use, and that choice of regularizer ends up affecting what the final objective is. And so picking the right regularizer is key and makes the difference between whether your final objective is actually tractable in off-policy stochastic settings or it's not. Okay, so with all that foundation laid, I can get started on the meat of this presentation, starting with distribution shift. So at the beginning of this presentation, I made this promise to you that, okay, there's this big challenge in off-policy RL, it's called distribution shift, and we're gonna actually approach this problem by regularizing the dual variables of our LP. So now I can show you how that's done. So we're gonna regularize the dual variables, so I'll start with the dual LP. Here it is, expressing the value of policy pi in terms of this optimization over D. And now there's a lot of choice in how we regularize this. I'll just reveal the choice that ends up working well. And the regularizer we're going to use is the F divergence. So we're going to fix some reference distribution D superscript D. And then the F divergence of D from that reference distribution is some function of D. And that function will act as a regularizer on our dual LP. So what's important to note here is that usually we think of regularizing with an F divergence as somehow encouraging the policy pi to be close to a reference distribution. But in this case, the regularization is really just to sort of make the duality work out. And actually, you can figure that these constraints here in a regularized problem, there's a constraint for each state in action, and there's also a variable for each state in action. And so the constraints uniquely determine that D star has to be D pi, regardless of however we regularize the objective. Okay, so now that we've got this regularized constraint problem, we can apply duality. And when we apply duality, like I promised, we end up with an unconstrained objective. So you can see now we're back in the primal space, since the optimizing variables we're using are in terms of Q values. The difference is that now our constraints are penalties, right? If you recall the primal QLP was essentially this expected initial Q values objective, and then these were constraints, right? These ended up being in the inequality constraints. Now, instead of constraints, we have penalties. And the form of those penalties comes about from the form of the regularizer we used. And conveniently, the regularizer we used, this F divergence from a reference density D superscript T, its dual form is the expectation over that reference distribution of F conjugate. Well, this is just the differential conjugate of whatever F you chose here. And so there's a lot of choice in what this reference distribution is. Almost no matter what reference distribution we use, these basic steps will hold. And the most convenient reference distribution for us is exactly the off-policy distribution we have access to, right? If we just set D superscript D to be the distribution in our replay buffer, then this objective ends up being just an objective for Q in terms of an expectation over our replay buffer, which is very convenient. And so now, given this, if we want to do policy optimization, we can do it in an off-policy way like so, right? We have an objective over Q that has an off-policy expectation and represents the regularized value of pi in the MVP. And then what we want to do with pi is we just want to maximize this regularized value. So this is the way to do policy optimization in an off-policy manner. You can algorithmically relate it to Q-learning and active critic, because what we're doing here is we're also optimizing a Q function to minimize some convex function of Bellman residuals. The difference from these standard algorithms is that our loss for Q is an off-policy expectation. Whereas if you do Q-learning and active critic, you can do an off-policy expectation, but that's the result of essentially just an approximation to an on-policy objective. Here, we don't have an approximation to an on-policy objective. This off-policy expectation comes directly from the neat properties of using convex duality and the fact that we use that F divergence regularizer. So this is one way that regularizing with a dual can approach the distribution shift issue. But there's actually another nice property that comes out from this. And it comes out from the fact it can be brought out when you think about what's the gradient of this inner objective with respect to pi. So imagine like we're actually doing policy optimization. When we do policy optimization, what we would do in the ideal scenario is first solve this inner optimization, get some Q star, and then for pi, we'll need to take the gradients of this objective with respect to pi. So what is the gradient? When we take the gradient of this objective, at some point, we'll have to handle this pi inside this penalty function. And so we'll do a chain rule, and the chain rule will give us some term that looks like this, right? The chain rule will give us the density of D superscript D, and then the derivative of F star of the residual. And then there will be some more terms from the chain rule. Now, conveniently, or perhaps obviously, this same expression is actually the expression for D star. So convex duality tells you that if you have Q star, if you've solved this Q problem, you actually have a solution to your original problem. And that solution, D star, has exactly the same expression. And if you recall, that D star is exactly D pi. And so when we do the chain rule, what happens is this off-policy expectation implicitly turns into an on-policy expectation over D pi. Right? The off-policy correction naturally comes from the Q star values. And so you get on-policy policy gradient from off-policy data. And it's important to note that when you actually implement this in practice, you don't need to think about all this math that's going on. It's really just happening in the background. All you do is just do backpropagation as you're used to. And it's really just the fact of how you train Q that gives you this on-policy gradient implicitly. Okay, so that's the first half of what I wanted to show. And now the second thing I promised you was with respect to this generalization challenge. And the fact that if we regularize the primal variables in the right way, that can be interpreted as approaching the generalization problem in off-policy RL. So now I can show you this. So we're in the primal LP, which looks like this to remind ourselves. It's an LP over Q values. And it might be interesting to think about at a high level and a sort of hand-wavy way, what does generalization actually mean in this LP? So as I mentioned before in the off-policy setting, we have a data set, but it doesn't cover all our states and actions. And so we can imagine, well, what would happen to this LP if we were missing a constraint for a specific state and action? Well, as I mentioned at the beginning of this talk, this objective over initial Q values actually pushes all the Q values down, and they're supported by these inequalities. And if one of those inequalities is missing, there's nothing to support that Q value. That Q value is going to go to negative infinity, and then you're going to end up with an estimate of your value of your policy, which is negative infinity. So this is bad, and you can imagine it can also blow up to positive infinity if you change up this min to a max. So how do we get away with this? We need some sort of regularization. And I'd argue that it's natural to regularize the primal variables by constraining them to be in some function class f, which is inherently low dimensional. So for example, we can take this function class f to be a unit ball in some reproducing kernel Hilbert space, right? And this way, we don't have to have, for example, a constraint over all states and actions. If we're missing a constraint in some state and action, as long as we have some constraints in state and actions which are similar to it, then there'll still be some support holding this Q value and keeping it from blowing up to negative infinity. So this is the regularization I'm going to use.
Ofir, I'm going to interrupt you for a second to say you have 3 to 4 minutes left.
Okay, thanks. So here's the regularized version of our primal, right? I've got the same primal objective, primal constraints, but then I've added this penalty, which essentially constrains Q to be a bounded LKHS node. And like in the dual, what we can do is we can apply convex duality and end up with an objective which is back in the dual space. It's in the dual space in the sense that now we're optimizing over this D distribution. But the difference is that the constraints are now penalties, right? The previous dual LP had this objective, and then these were constraints, and we were constraining them to be exactly 0. Now, because we had this convex regularizer, the norm constraint, the constraints in our dual are now in the form of penalties. And that penalty is in the form of the RKHS norm. So we're really penalizing the dual objective with the constraint violations as measured in an RKHS norm. So we've got an unconstrained objective, but it's still a little unwieldy with this RKHS norm. But obviously, there was a reason we chose an RKHS norm, and it's because we can apply the kernel trick to this penalty and get a nicer form. So specifically what happens is you can interpret what's going on here as you're really measuring the MMD distance between D, which is some distribution, and then this transpose Bellman operator applied to D, which is some other distribution. And so you can write that instead as a sum of expectations of kernels, right? Where you have an expectation over 2 samples from D, you have an expectation over 2 samples from this transpose Bellman operator, and you have an expectation over 1 sample from each of these. And now we have nice expectations, and they're a bit more tractable than optimizing this directly. So clearly there's a choice in what kernel you use, and I'm not going to pretend to know what the best kernel is, but there's a lot of interesting choices. For example, if you want to choose the energy distance kernel, you get interesting expectations over distances of state action pairs. And in this way, we can see that that original regularizer we applied, whose motivation was to impose some sort of generalization properties on the Q values, shows up in this dual objective in the sense that this dual objective is now representation aware. And the distances of states and actions appear in this dual objective. But again, good representation is key, and certainly it's still a big open question what the ideal representation or what the ideal kernel should be here. Okay, and then the last thing I wanted to show you about this generalization aspect is how to make it off policy, right? So we've got a nice representation-aware objective for the dual, but all the expectations are over these distributions we're learning, D and the Bellman transpose operator applied to D. But it's pretty easy to make these all off policy by just applying a change of variables. So instead of optimizing over D, you can optimize over zeta, where zeta is defined as D divided by your off policy density. And then all these expectations nicely and conveniently turn into off policy expectations, right? So now the D dot R term turns into an off policy expectation of R, but weighted by zeta. And then all these expectations turn into off policy expectations of the kernel, but again, weighted by zeta. And so this is ends up being a fairly practical and tractable objective for off policy settings. Although there still is this annoying square root term, but usually you can hand wave that away as well in practice. Okay, but that's all I wanted to show you. And as a summary, what I showed was the distribution shift problem can be attacked by regularizing the dual variables. The generalization problem in off-policy RL can be arguably attacked by regularizing the primal variables. I've listed a small subset of works which I think use these tricks. But certainly there's a lot of other applications to use these tricks. And I think there's a lot of potential future work in, well, one, how to apply these tricks, which I've shown you, and two, other choices of regularizers, which yield even better objectives or better resolving of these challenges. But that's it for me, and I'll take any questions.
Thank you so much, Ofir. This is fantastic and a beautiful complement to the morning's talk. I believe that we have a question from one Gergely Noy to start, followed by a question by Jacob Buckman. So I'll start, Gergely, today. Go ahead.
Yes, that's right. Thank you, Mark, and thanks, Ofir. I really love this work. So I have a question regarding your regularization of the dual variables. So one issue that I see here is that it may be actually difficult to get unbiased estimates of the gradients using only samples, right? Because your objective function is a nested expectation, right? It's an expectation of a nonlinear function of a conditional expectation.
Mm-hmm. Yeah.
Right?
I agree that's an issue, and I glossed over that issue. Yeah, this issue that this really is an expectation inside a convex function. And yeah, I think the best way to get around that that's known to me is just to optimize the Lagrangian instead of the full convex dual. And when you optimize the Lagrangian, you also get the same nice properties, like you get the same on-policy gradient property.
Right. So, but does that really result in like a practical algorithm in the end for like large scale settings? Is it easy to parameterize the dual variables?
Yeah, in practice, in my experience, using the Lagrangian complicates a lot of things in the policy optimization setting. At the same time, I'm hopeful that, in my experience, has been very short, and I'm certainly not an expert at really scaling out the algorithm. So I think it should be doable. It's just an open
Right.
problem.
So there's still work to be done. I guess that's the bottom line.
I have a follow-up question for you, Ofir. You have implemented this in stochastic environments, and it did do something. So that there's empirical evidence that this is okay.
Yeah, yeah. In practice, what we do is we just sort of eat the bias or ignore it and optimize this objective as is, and that works better than doing the right unbiased thing.
Right. Gotcha. Thank you.
Any other questions from? Maybe I'll actually take the Q&A question. There was a question by Jacob Buckman from earlier, which might be actually answered by the generalization point you made, but I'll ask Ofir. This exact formulation you have here right now, won't it simply learn the optimal policy for the empirical MDP given by D? So how does this correct from statistical error introduced by finite samples?
Right. So, yeah, so my generalizations ignore the statistical error issue. What you can do, well, there are ways to introduce statistical error, like, well, one straightforward way is to think of this, as I mentioned, this is just like an MMD, right, between D and the transpose Bellman operator applied to D. And there's lots of literature in the kernel field about you have two distributions, you want to compute the MMD, but you only have finite samples, and how to get confidence bounds and other things based on that. So I ignored that issue in the presentation, but it is approachable by standard methods.
Fantastic. I'll take maybe a live question if there's one. Okay, let me ask Matisse Federico's question, which is the restriction to some function class made me think of the talk from Emma. Can you regularize by basically having policies that have enough coverage? Is that something you've looked into?
I hadn't thought about it before. I guess thinking about it now, I guess the question of regularizing in the policy space makes me think more of like regularizing the dual variables. In some sense, like the regularization on the dual variables with the F developments is a penalty form that regularizes the policy to be within the support. But yeah, I guess you could turn it into like a constraint on the policy and some other things and make it work out and have nice objectives. But yeah, I hadn't thought about it properly yet.
In fact, I think Nanjiang is going to jump in and tell us that there is in fact a connection. So maybe Nan
yeah, can people hear me?
For sure.
Yeah, hi, Ofir. Great talk. So actually, I think I have some answer and comments / question, which is closely tied to all the questions being asked like so far. So I think it's interesting. So basically, we have realized that in our most recent paper, that algebra actually, in some sense, solve the problem that is asked by that is discussed by the talks earlier, right? When you don't have sufficient coverage in data. So what's very nice is that if you look at the algebra and what happens when you don't have data support, the optimization, well, actually it's central algebra, right? So you add yet another decision variable to model marginalized importance weights. So in this cases, your optimization objective for a given pi is precisely a lower bound on the policy value of a particular pi, where how loose the lower bound is depends on how good your data coverage is. So we thought that's extremely promising. So we actually wanted to try to run the algorithm in that setting. But again, when you have that additional decision variable to model importance weights, you get max pi, max, something like max pi, max q, min zeta or something. And holy shit, I just have no idea how to optimize it, and neither do we have any empirical success. And I want to pick your mind on this. Is do you think the optimization aspect of it is still promising, or we just need to like look to something else to solve this problem?
So I think I guess fixing the optimization directly, I think, is interesting to me. I guess like the few properties of the optimization which we can point to as being bad and maybe the sources of issues. Like one issue is like this optimization over pi doesn't interact well with the Q or zeta because it's not like jointly convex in terms of pi and Q or things like that. And there might be ways to approach this, like instead of using the QLP, using the VLP directly. At the same time, I'm not sure if these issues which are more theoretical are actually the source of a lot of practical issues. So at the same time, I feel like an interesting other approach to this optimization problem is to perhaps take a lot of the insights that come from convex duality and a lot of the compelling objectives, but instead see how we can get these insights and compelling objectives applied to the existing and well-performant standard dynamic programming algorithms. And I'm not sure what's the best way to do this, but I think maybe it should be feasible in the sense of like, can we take the insight of like this on-policy gradient property in algebra and other things, and can we apply it to dynamic programming without having to get into the optimization difficulties endemic of doing all these mins and maxes?
Okay, fantastic. Well, thank you, Ofir. Thank you again for the talk. And so this concludes, in fact, the talk portion of the day. So thank you again, all the speakers.